The amount of attraction between ions in an extended ionic lattice can be measured using something called the lattice energy. And the lattice energy is a measure of how much energy is needed to fully separate 1 mole of a solid ionic compound into its gaseous ions. And these lattice energies tend to be very, very large. And as a result, the ionic compounds tend to be very hard to break apart. So I'll give you a couple of examples now. So in this example, we've compared the different lattice energies of the various sodium halides. So sodium fluoride, sodium chloride, and sodium bromide. And you might notice a trend in decreasing lattice energy as the anion gets bigger. And we can show you another set of examples. In this case, we have chloride as the anion in both cases, but the cation changes from sodium ion to magnesium ion. And there's a very large change in lattice energy. And we can explain this if we think about how electrostatic attractions work. Lattice energy is very much proportional to a standard electrostatic attraction. So we can write the following, which is that lattice energy is proportional to the charge for one ion times the charge for the second ion divided by the distance between those ions. So if you look at the examples of the sodium halides, Q1 and Q2 are constant. Right? In each of these sodium halide examples, the charge on the cation is plus, the charge on the anion is minus. So Q1 and Q2 are constant values, only the distance between them varies. So the sodium ion is constant in size, but the sizes of the halogen ions will change. Because bromide is the largest, the distance between the center of the bromide ion and the sodium ion is going to be larger than the distance between the chloride and sodium or fluoride and sodium ions. And that means that the lattice energy for sodium bromide has to be smallest. So in the case of sodium fluoride, you're dividing by a fairly small distance, so you'll have a fairly large lattice energy. And in the case of sodium bromide, you're dividing by a fairly large distance, so you'll have a fairly small lattice energy. In our other example with sodium chloride and magnesium chloride, things get a little bit more complicated. So with sodium chloride and magnesium chloride, we have to consider both distance between the ions and the charges. Sodium ions are single positive charges, while chloride ions are single negative charges. But in the case of magnesium, magnesium is a 2+ charge associated with chloride ions, which are single negative charges. So our lattice energy expression changes a little bit. So for sodium chloride, it's exactly like the lattice energy expressions we wrote earlier. 1 positive charge times 1 negative charge, and we've omitted the signs here because it's the magnitude that's important, not the actual sign. But 1 positive times 1 negative divided by the distance between the sodium and chloride ions. For the magnesium chloride, it's 2 positive for the magnesium times 1 minus for the chloride. Again, we've omitted the signs. And that's divided by the distance between the magnesium and chloride ions. And it's kind of important to note here that interionic distances, so the distances between ions, are only going to vary over a fairly limited range. You don't typically find ions that are double or triple or quadruple the size of other ions. It's usually a fairly small difference between ion sizes, or at least relatively small. But when you consider charges, charges are always going to change by integer values. So the difference between 1 and 2, or 1 and 3+ charges, or 2- charges, you're going to have fairly large iterations. It's not going to vary by some small fraction of a charge. It will differ by integers. And for that reason, changing a charge has a much larger effect than changing a distance between ions. Because when you change a charge, you're multiplying different integer values together. So in the case of sodium chloride, 1 times 1 is 1, divided by the distance between sodium and chloride. And in the case of magnesium chloride, 2 times 1 is 2, divided by the distance. So we can see in this case that the lattice energy for the magnesium chloride is going to be bigger than the lattice energy for the sodium chloride, because the numerator is double. And yes, the distances between ions are going to be different, but unless the distances differ by a very, very large factor, the charge is going to be the more important issue.